Okay. You still see it? Yeah. Okay. Good.
So
this
15 minutes.
Yeah, sorry for the delay. So I don't need that much time because a lot of the things that we have discussed in the past about how these assigning value to heterogeneous pledges could work is now covered by the tool chain that have been just presented. So heterogeneous means here everything but x86-based WLCG grid sites. And the important emphasis is pledges. So this means resources that are accounted against what we get. So computing for science is changing. Scaling of x86 generates little benefits in single core performance, and many different paths are taken to get more performance. So like many core vector, larger vectors, GPUs, TPUs, FPGAs, and so on. And in addition, grid, cloud, and cluster computing are now completely commodified. And that means there's no incentive for funding agencies to invest in their evolution. This is done by businesses. And what's also on the horizon is that several exascale computing projects are very far advanced. They all use different advanced architectures for which we have not prepared very well. We couldn't because it was not known. But this is where the public funding is directed at, because this is enabling new things that could be done, and the risk for these machines has to be kind of supported by the public. And this is also what subsequently will be given to science and to us as pledges on the longer term. So the WLCG management board asked the cost modeling and the benchmarking working groups to try to understand how these resources could be accounted for, like comparable to current pledges. And after many discussions, first results were presented in October at the GDB. You can follow the link if you want to see what was said there. So I just summarized the concept. For details, you can go back to those slides. It's based on to measure the throughput for experiment workloads, and only for those that can run on these systems, because for others it makes no sense. For example, if you would now run the standard set that is in HAPSCORE, many of them would give very, very little throughput. And from that, a quantity is derived. It's called capacity, so the name can be changed, of course. And this is based on to use accelerators if workloads exist that can use them, use CPUs and accelerators in a way to maximize the throughput. This means also that some components will not be used, or some fraction of them. And these are also then not taken into account. This could be either for lack of code, the cost of data movement, the limitations of schedulers to give fine-grained access. So this will not impact the value you get. And these throughput measurements then can be converted to HAPSCORE by looking at the events per second that you get for the supported workloads, or by to the classical HAPS-spec06 by comparing the throughput with an x86 system with known ratings. So the details of how this is done can be seen in the link and in the appendix. So the core idea is only workloads on these new resources that can run are taken into account, and only their throughput is taken as a basis for valuing the pledges. So this sounds like a lot of work, but in fact, it's actually not a lot of additional effort, because this is part of the necessary adaptation and validation process for new heterogeneous systems. If you get an HPC, you first have to get your workload running there, and also to understand how well it runs. And as part of this, running these benchmarks workloads is only a small fraction. In addition, the number of very large heterogeneous system is limited. and they are in use for a couple of years. So this means you don't have to do this on hundreds of sites like in the grid. And also accelerator vendors are motivated to provide somewhat stable APIs because people don't want to see their investment in the software go away all the time. So then this is not all, because if you do this, you will get on very expensive systems, sometimes very poor throughput rates. And it's important to understand actually how far away from the optimum we are. So this is not to value the resource, but to get an idea whether it's worth using it. And even on modern x86 machines, the HAP code only utilizes a fraction of the potential operations that the machine can deliver. One of our fellow did a lot of measurements with HAP workloads to see how many instructions per cycle we actually use and how this compares to scientific code like weather code, and we use only a small fraction. So to address this, the concept of a realized potential has been introduced, and the goal is to get an idea how well the HAP workloads can actually exploit specific systems. It's also an economic argument. And it starts with using HPC benchmarks such as LINPACK or LAPACK to measure the maximum potential of the resource. This gives you a number of floating point operations that corresponds to the pledged time on the machine. And the ratio of the used operations during the throughput measurements and the theoretical max gives then the concept, the value for the realized potential. So details on this are also in the slides. An alternative is to compare these with a reference x86 system, for which we also know the LINPACK and LAPACK ratings. And the motivation there is if these comes out very poor for a very expensive machine, this can be a good indicator that investment in software development is needed, or that the funding agency should focus more on other sciences on these machines. So, however, all this, I have quite a few concerns. One is the usability. And this is the ability or cost to integrate the resource into the workload data management systems. And this must be in the future taken into account. A workload well packaged like our benchmarks now might be runnable as a proof of concept in a containerized version. And this would give you a realized potential for pledges. However, due to the constraints of these resources, like limited access to external network, authorization, the resource might be of limited practical value and very difficult to integrate into the experiment's workflow management systems. And there are potentially significant costs for users to build the necessary bridges and tunnels so that it can be integrated with the workflow. And right now, this is ignored, but it's also mainly ignored because these resources are not given as pledges. So we basically are not, in quotes, paying for them. The other concern is at the moment, only very few production workflow exist that support many alternative or several alternative architectures. And most of them also only support a part of a workflow. For CPUs, this can be improved with some effort, like building and validating, but this includes also physics validation. It's already quite an effort. For the GPUs, FPGAs, and TPUs type of resources, this requires a massive software redesign. You cannot just translate it. One has to use different approaches, different algorithms. And this will cost a lot of effort. But given the current trends, this seems to be the most likely future we have to cope with. And I'm not sure that we are really in a good position in this timescale of 2021, when the first exascale systems arrive, to accept them as pledges. I think we are far away from that. The other concern is, and it's a little bit what Martin mentioned, we ignore in all this a lot of hidden assumptions. So when you use a resource, standard grid site in WLCG, you have a lot of things that you take for granted, like a defined minimum amount of memory per core, that you get an idea that the resource is accounted by something that corresponds to your workload. And also many other aspects are well defined, like that there is local storage or at least fast access to some, that you have network access, that there are edge services like CVMFS. And on HPCs, and you cannot assume most of these things. So they are all basically, it can be anyway. And if they are given as paid resources, this really matters because it will affect our throughput. So containerized self-contained workloads don't assess also the complete system. This is a great advantage for purchasing. And it's also corresponds largely to what you get on grid-like systems because they have been built for our workloads, but it's not necessarily related to the production throughput you will get on these heterogeneous systems. What I mean with this is easy seen if you, or can be seen if you look at a simplified view of a resource as we use them in the grid. You have a wide area network, you have some parts and bits in your computing element, you have a scheduler on the side, and you have some local store. If you go to heterogeneous resources, most of these can differ in the technology used, the protocols used, the access rights you have to them, or whether they are all there, and what type of granularity of access they allow you. And all these impact the throughput of your system. But with our packaged workloads, we only measure these in case supported workloads exist, so only a small fraction. This means we measure something that is important to measure, but we don't measure the whole story. So this leads into the discussion. So the questions that we should, in my view, discuss is what aspect of a system should throughput-based benchmarks for valuing a pledge in the future cover? So what does this mean for the HPC system? And how do we expand it that it uses more? Should we run reference workloads that also come with reference data? I don't know. But in a way, the impact of local disk, site storage, access to a wide area network, somehow, in my view, is not so clear that we can ignore this. And then how do we handle in a more formal way the usability aspects when we value pledges? So these are clearly costs for the users, and to ignore them completely, I think is a bad idea. So, but this needs to be discussed how this can be done. That's all. And we have another one. I think this one has been put by Domenico.
Yes. So,
yeah. So
this
maybe
is related to what I mentioned before. So first of all, is related to what are the constraints that we will face during the installation and running of the benchmark. I was mentioning before that we cannot assume many things that we find in our standard WLCG sites, but probably it's just because we are trying now. And those are typically problems that also in workload management system have to be solved. So we could wait as a benchmarking working group and they get solved, or we can anticipate them together with who takes care of the workload management system.
I think this goes in lockstep. So in a way, measuring a resource or investing the work to get a resource integrated into the experiment's workload management before we have an idea how how well it reacts to our specific workloads is not worth the effort. So it's clear that first the benchmarks have to run before we can look at the other thing. But then the experience gained to run the benchmarks can be also used to speed up the process to integrate these resources into the workload management systems.